Okay, so we're going to resume now with the PTTI keynote, and we are fortunate to have Dr. David Scherer. He leads the timing and complementary PNT activities at the MITRE Corporation, spanning applications of atomic clocks to quantum sensors. He holds a Ph.D. in Optical Sciences from the University of Arizona. The floor is yours.
Thank you very much, Juan, for the introduction, and thank you everyone for being here. Make sure this works. Okay, so I'd like to share some material, some big picture ideas about the field of commercial atomic clocks. And these are ideas that I've been thinking about for some time that really started when I was at Symmetricom Microchip. There I had the opportunity to be a lab scientist in the R&D physics department working on several DARPA-funded projects related to next-generation atomic clocks. Got to work alongside the factory in CSAC and rubidium clocks, hydrogen masers, cesium beam tubes, a whole slew of different commercial products. Since I've been at MITRE for 3 years now. I'm now on the government side, advising many US government sponsors in applications and future directions for clocks. So there's a couple people in the US that have worked in both in the commercial side as well as on the government side in the field of atomic clock products. I've talked to all of them. It's a small group, and I'm really happy to share some insights that I have from incorporating both of those two directions in the field. So that's where we're coming from in terms of my background and what we want to share. So the ideas we want to share are, how good can commercial atomic clocks get in the near future? Who cares about that? And how does clock quality scale with size or weight or power or cost? What are some of the physics package architectures that are best suited for future innovations? These are some of the themes that we'll be talking about. So here's the main idea. We can make clocks better. When we make them better, they'll enable a whole slew of new applications which we're not even really aware of today. We're not doubting that clocks can get better. Right? But we want to put a little bit of realism into how much they can improve in the near term. We often hear these reports in the popular press, performance like a cesium beam tube, in the size of a raspberry. And that's not very likely. Instead of focusing on these kind of pie-in-the-sky improvements, we'd like to make recommendations for making the entire industry better, with specific recommendations for government, industry, academics, national labs, and standards organizations, all aimed at improving the future performance and quality of these commercial products. So I'll start with a disclaimer. This talk is about industrial atomic clock products. And it's kind of annoying to keep saying those 4 words for the whole time. So I'll just say atomic clocks. But what I'm talking about is commodity electronics products a regular person can buy by picking up the phone, calling a company, and placing an order for a lot of them, like 100 of them. Okay? Like commodity things that you can find. We're not going to be talking about recent demonstrations that are funded by DARPA, custom one-off space clocks, academic demonstrations, high-performance laboratory frequency standards, the whole slew of different things. Non-atomic oscillators. We're really focused on commodity electronics products for the bulk of the material that's in the presentation, which I may accidentally call atomic clocks, but we're specifically talking about products. Of course, those products are a subset of a much bigger class of systems, the whole slew of atomic frequency standards. Thankfully, since we're at ION, we don't really need to justify the role of atomic clocks. This is well familiar to anyone attending a PTTI conference. Atomic clocks underpin many different aspects of how we function in modern society, from navigation to communications, sensing, power grid, financial transactions. All of these are enabled by time and frequency from atomic clocks. And that's not special. There are a lot of other products that have revolutionized the world, changed the way civilian and military life operates. What's special about clocks, though, is the number of clocks that are used to have this global impact. So, again, clocks aren't special. There's a number of physics-based, sort of Nobel Prize-winning physics innovations that have changed the world. Here's my short list: transistors, lasers, digital cameras, fiber optics, LED. There are a lot of things. Like, the world is different now because of these things. But atomic clocks are different because most of these, you need the thing at the point to do the thing that you're talking about. Transistors, for example, you need a lot of transistors at the location that you're at to do the thing. Clocks are different because time transfer is good. So it takes a really small number of clocks to have a big global impact. Case of GPS, for example, depending on if you count the cold spares in space and how many ground stations you count, it takes like 200 atomic clocks to operate the whole constellation, space and ground. It's not the case in these other innovative products, right? And that has ramifications for the industry. Because of that, there's a small number of companies that are interested in this field. It's a slow-moving, stagnant field because time transfer is good. We'll see some of the economic and sort of pace of growth innovation impacts as a result of that as we keep going. So, transition here to talk a little bit about evolution of commercial atomic clock products over the past several decades. So this is not intended as a history lesson. If you want to really understand the history of commercial clocks, I'd recommend 2 excellent review articles by innovators in the field, which I've referenced here. But here's a snapshot. Right? The first atomic commercial clock product was introduced. It's a cesium product by the national company. It's called the Atomicron. That was in 1956. Rubidium products followed shortly thereafter in 1962 by Varian. And today's sort of baseline high-performance atomic clock, the Microchip 5071A cesium beam tube, was initially developed by HP, introduced in 1964. There have been several innovations and improvements, but the basic architecture was introduced commercially in 1991. The product has not changed much since then. That's not the case in rubidium standards. There's been a lot more diversity in rubidium products, and the field there is really split into 2 different halves. There's sort of lamp-pumped rubidium clocks and laser-based coherent population trapping clocks, which could be rubidium or cesium. What we'd like to be able to do is compare these clock products, not longitudinally, not over time, mostly because we don't really have great access to many of the old data sheets, but vertically. So I take a snapshot of the field at 2020 and look at how different products compare to each other. And so we set out to be able to do that. What we tried to do when we started looking at this a couple years ago was to come up with sort of this global quality factor for clocks, this goodness parameter. What we wanted to do was plot a single metric related to the clock quality as a function of a single resource metric. And we got stuck because there's not a great way of doing that. Different applications require different quality parameters. Some favor short-term stability or long-term. Some favor time error, accumulated time error, or environmental susceptibility, low susceptibility. There are many different kinds of quality factors. There's also not a single well-known resource metric. Some applications require low size. For some, power is most important. For some, cost is the most important thing. There's not a great way of doing this simple apples-apples comparison. But it's our job. That's what we have to be able to do as a community to make these comparisons and to track our progress. So we're going to try to do it, even though it's imperfect, the solution that we've arrived at. The problems that we came up with, there's no single the cost function, there's no single performance metric. Even if we had this, what time interval to use? Am I looking at the stability after a second, a day, a week, a month? Different applications require different time intervals. What environmental profile to use? It's not, it's definitely not fair to look at a clock at room temperature if you want to put it in the field. It's also not quite fair to evaluate it over from minus 40 to plus 80, some enormous temperature range, because many applications don't span that either. So we're going to try to do this even though we know it's an approximation. Thankfully, there's a well-established equation for computing the time error for different clocks. This is well known in the community. It involves a deterministic part. We're looking at the time error as a function of holdover time tau. We'd like to look at that after a day. The deterministic part just looks at the initial time error, the initial frequency error. There's some known deterministic drift shown with this capital A. There's some environmental part due to the integrated effects of the environment. And there's this plus or minus this random or stochastic part associated with the clock instability. And so great, okay, we have an equation. Let's try to use this, right? This is the equation that we wanted to be able to use. And when we tried to do that, we ran into a couple of problems. So I'll just highlight an example of how we did that for one particular clock. Out of any, we just picked the Microchip CSAC. We went to the data sheet. We saw a single number for deterministic drift. We saw an Allen deviation number related to the clock instability. We didn't find it at a day, but we have it at 1,000 seconds, so we can extrapolate. We saw a temperature sensitivity, over this enormous temperature range, minus 10 to plus 70. You're like, all right, well, it's not quite fair to linearize that, but taking such an enormous thing would be really a worst case. So what we chose to do, this was an analysis decision, is just to use this very simplified equation, which ignores the initial sync and just has deterministic drift, and it adds the 1 sigma value associated with the Allen deviation to factor in the stability. A number of assumptions. You can read our IEEE review article if you want to go through all the details. I won't focus on the details. I'd like to focus on the result. And so we did this for a number of clocks in the market. And I'll spend a little bit more time talking about the results. So first, we computed an enormous clock database. These aren't all the atomic clocks on the market, but we made an attempt to include at least one from every major manufacturer in the world and at least one of each category. We've also color-coded them by type of physics package. CPT is a laser-based coherent population trapping clock. Rubidium means a lamp-based rubidium clock. Cesium is a cesium beam tube. There's 2 cold atom clocks. There's a single passive hydrogen maser and 3 active hydrogen masers. We now plot the time error after a day based on the previous equation as a function of size. It's a log-log plot. The legend is shown here. Again, emphasizing TempCo and environment is not included here. That would only make things worse. When we did that, we saw something really fascinating, which is that every single clock on the market fell on this linear trend line, that's power law on a log-log plot, to within an order of magnitude. This is way more than we knew there would obviously be a trend. We didn't think it would be this predictable. A few ramifications that come out of this. So first, we don't really care about the individual clocks anymore, and it's kind of cluttered to have all these numbers here. So we're just going to take off the legend for the rest of the talk. You got one last second to find your favorite clock and try to remember where it is on the plot. But we're going to take off those legends going forward. What I also want to plot, and this is starting to get a little bit US-centric, when that's okay, is 5 different US government clock development goals over the past 20 years. These are not included in the trendline fit, but I want to put them as black stars, as goals, not as demonstrations, just to see the difference between US government clock development goals and what we have now in commodity electronics products. We can also plot it versus weight. There's not much to say there. Size and weight are very correlated in electronics products. And, we see the same trend line. I don't have shown the exact equation here that's in the IEEE paper. The exact equation doesn't really matter. What we think is fascinating is that there's such a predictable and persistent scaling We're not saying that it's a fundamental physics here. There's not any fundamental physics that we've done. We've just done a phenomenological, empirical observation of what's on the market today. We'll come back to some conclusions from that. So the next one we did was look at clock performance versus power, where we see a different type of scaling. There's no longer a power law fit here, and you see this sort of curving or nonlinear on a log-log plot scale. So there's some kind of thresholding or saturation effect that's going on here. Empirically, we can see we need to invest a few watts, something like on the order of 5 or 6 watts, before we start reaping some benefits. Benefits means less time error. Better is down on this plot. That may just be related to the fact that we need to have some threshold amount of power to run the microprocessors and controllers and everything we need in atomic clock products. There's, interestingly, a little bit of a gap here in the region of like 1 to 5-ish watts for clock products, which might be something that would be useful to explore. Okay. I'd like to talk a little bit about what this means. Some of the themes that we've got from the Trendlines and from our discussions with folks in the community. And the first one is both obvious, but I think it's also very interesting. It's commercial atomic clock products exhibit a predictable performance scaling. And that's obvious, right? Any product is going to scale with resources, whether it's cars or photovoltaics or atomic clocks. We're surprised at how persistent it is across 5 or 6 orders of magnitude or size or weight or power. And we're surprised it's so persistent independent of what technology we're using. From very, very ancient rubidium and cesium clocks to very modern physics-based, laser-based CPT clocks, cold atom clocks. This is what surprised us. And led us to our second conclusion here is, it doesn't matter what's in the box. So at some point you have a black box, you plug it into the wall, you have some atomic resonance on the inside, and you have stable 10 megahertz coming out. On the inside, in our trend lines, we've included passive atomic frequency standards, active atomic frequency standards, rubidium, cesium, hydrogen standards, lamp-pumped, laser-based. Atomic clocks that use very cold atoms cool down to temperatures very close to absolute zero. Atomic clocks based on room temperature or heated atomic beams. It doesn't matter. In fact, there's a very, very clear seamless transition between these laser-based and these lamp-pumped rubidium clocks shown at this inset. So if this happens, it's not really about what physics package architecture is best to pick for future clocks. Really that at some different size point or some different power point, there is an optimal physics package for that power point, but there's not a single one that's sort of like the global best. We see empirically that investment of a few watts is required to get this thresholding behavior. And we also notice, in terms of the innovation in the past 20 years, that innovation is really at the edge. We're seeing a lot of movement and new products in the low performance, or low power end CSAC, as well as some of the higher performance, some of the cold atom clocks, without much change in the middle. It would be interesting to pursue this beyond the extremes that we have today. Even lower powers, and potentially even higher performance for optical clocks. So those are the themes that we see from the trend lines, and we can come back and talk to that a little bit more later on. I'm going to shift gears and talk not about the output of the industry, but about the input, like what's coming into the industry in terms of US government investment. And now we're going to get a little bit more US-centric as we talk about financial investments from the US government, but I believe this scales globally. So what we attempted to do was come up with a list of all the atomic clock development programs from the US government over the past 20 years. It's definitely incomplete, right? Because it's easier to miss something than over-include. But we tried to make a good faith effort to get the right number of zeros for all the big clock development programs. You've heard of some of them, things like CSAC, right? Several other DARPA programs are included. We arrived at this list in a number of different ways. Some are publicly available information. The DARPA budgets, for example, are well known. You can Google them. Some are available from discussions with colleagues. Some I just estimated, right? So there's different quality of information that went into this list, but we're trying to get the right number of zeros to add up the dollars that went into this industry in terms of funding. And that number we estimate to be around $400 million over the past 20 years. So it's worth asking, what are we getting out of that? And we'll try to come at some kind of analysis of that value, right? So the US government, in our view, has been investing heavily in atomic clocks since 2000. Started really in earnest with the DARPA CSAC program. That started in 2002 and ran in sort of different forms till 2014. This resulted in the introduction of a commercial product in 2011. That's amazing. Less than a decade after the release of a DARPA BAA, Symmetricom released a product, shipping from a factory. It's a huge success story. Since then, a second source, Teledyne, has introduced a similar product. And I would say there's many different indirect outcomes of the CSAC product, including the Mac product and really many other CPT-based products on the market. Now, since then, there have been a slew of other clock R&D development programs in the US. Impact, ACES, STOIC, various small business innovation research programs, funding by others, but there's really been no volume commercial or DoD product that's resulted from this R&D activity. And that's actually what got us thinking about this sort of return on investment analysis. With an asterisk, I do want to point out a newcomer alert. Spectrodynamics, a small company in Colorado, does have a portable cold atom rubidium microwave clock. Franklin's here. Say hi to Franklin. Please go talk to him. It's a really cool product. I encourage you to go learn more about this at the exhibit hall. It's a little, from our perspective, it's a little bit of a stretch to call it a volume product right now. There just haven't been enough of them that have really been tested. So one big thing came out of this with some similarities, and then maybe one asterisk, one other maybe. Right? So the question is, are we getting our money's worth? So let's look at the value generated from this. So here's my poor PowerPoint description of all the R&D that happens in the world in atomic clocks. Right? This is what it looks like. It's a box, right? There's universities, national labs, FFRDCs, companies. Many folks are working either in atomic clocks or in components related to clocks that's part of this. And I'm kind of mixing US and global here, but we'll focus on the US. What's getting pumped into that to keep that alive? US government investment at the tune of around, let's call it 20 million a year. Let's just linearize it. Okay, 400 million bucks over 20 years. Industry is also investing. Industry has an R&D budget. It's small. I have no idea what it is, and they probably won't tell us anyways. But industry is pumping some money into that. All right? These are the inputs into the box. Shown on the bottom are not financial inputs, but they're drivers, they're pushers, right? There's known DoD needs. Like if DoD releases a BAA that says, we want you to do this, industry is going to work towards a product that does that. There's from our view, there's a couple of really strong drivers right now. There's low-cost CSAC. People want a CSAC that costs small hundreds of dollars. There's future high-performance space clocks, future space capabilities, and many others. But these are the things that we see as sort of known drivers. There's some unexpected ones, which are interesting. And I'll share a Microchip story. If you talk to the folks at Microchip, Peter Cash is here. I encourage you to talk to them about this at the exhibit. They'll tell you that the market for CSAC now, the biggest driver in the market is the oil and gas industry. It has been since the beginning, and it still is. And that was unexpected. No one from the government team or Symmetricom, Microchip, expected that at the beginning. But because of that, the oil and gas industry kept the factory alive, kept people employed, kept engineers building and designing circuits, kept scientists employed, so that over the course of 5 to 10 years, we now have a better CSAC that could potentially become a more high-volume DoD product. And this is a relationship we think is worth exploring in more detail, that kind of synergy between government and industry needs that may be being sort of underutilized at the moment. I don't know what the others are because they're not expected. So we can look at what's coming out of this. This is my box of R&D. Money coming in, needs coming in, what's coming out? We tried to estimate the size of the global atomic clock market. We did that by talking to a number of folks in the industry, trying to read industry reports. There's not a great way of doing that because we don't have global numbers. We heard numbers anywhere from as low as 100 million to as high as at 450 million. This is US dollars in revenue per year. So you could just take the midpoint or something like that. If the US market's a half-ish and DoD is a half-ish of that, trying to get the right number of zeros here, DoD purchases tens of millions of dollars of clocks per year. That would be equivalent to a couple GPS clocks. And so if you just look at the numbers in a very crude way like that, you might say, oh, something's kind of weird here. So we're putting $20 million a year, but DoD is only using 10-ish million a year. Are those in the right balance? That was the question we set out to ask. And as we got further in that, we realized that that's not really a great question to try to answer because there are many other benefits that come out of this that are not captured in clock revenue. Right? Clocks are typically used as components in larger systems. We know the global market for GPS is north of $1 trillion since it was developed. This is a system that's enabled by atomic clocks. Future capabilities, especially war-fighting capabilities, if we could end a war a week early with clock capabilities, that's something that's difficult to put a financial value on. Workforce and component development of all the folks in the government who are using clocks in larger systems or PNT in larger systems is also something that's extremely valuable. So I'll just say MITRE is beginning to start to work on this economic analysis of the overall economic impact of atomic clocks in society and trying to help scale the appropriate value of investment. That's something we just started. I don't have anything to report on that today, but we'll be able to share that as time goes on. So I think I'm going too fast here, but we have a few slides now on the path forward for the clock industry as a whole, looking at government as well as industry for recommendations on how to make clocks better. The first one is, and really the most important, one of the themes of the talk, is it's important for us, when I say us, the whole community, to develop realistic goals. If we look at the entire state of the field in 2022 right now and see that it follows this persistent and predictable trend line, and then we come out with some requirement or some goal for some future system, not a custom one-off thing, but a volume shipping thing that's, this pink star is way, way off the trend line, it's kind of like going from couch potato to a gold medal in a couple of years. It's not very realistic, and it's not super helpful for the field. We don't think this trend line is static. All right? It's not fundamental physics. That line is not going to be there in 50 years. What we predict, and I'll be happy to come back in 10 years to give a 10-year update on the trend line, is as physics packages, as laser technologies, as ASICs get better and better, individual clocks will start creeping down below the trend line. slowly over time, and at all size scales, at all power scales. And slowly what will happen over the decades-long time scales is that the entire trend line will slowly start to come down and down and down. It may change slope. Slope doesn't really matter over the course of time. We view that future as much more realistic than a single company issuing this sort of leapfrog technology that's going to jump over everybody else and issue a volume shipping commercial product next time like that. That's a prediction, and we'll be happy to come back and look at the validity of that with a little bit more time. In order to get there, we have some specific recommendations for improving industrial atomic clocks by, say, 2050. 4 specific ones. First, adequately incorporate commercial interest in government development programs. This is what we learned very strongly in the case of CSAC. There's a tendency for anyone to just think about what they want, right? And we're seeing specific needs from DoD coming out, like low-cost CSAC, future high-performance space clocks for GNSS and other applications. There's some really interesting potential markets in the commercial sector, and not necessarily markets for clocks, but sort of market levers and pushers. We even heard about one this morning. I mentioned the quantum computing market. So there's multiple US-based companies in quantum computing with a market capitalization higher than the global atomic clock market. Okay? Now, quantum computing is a bubble. It's overinflated right now, so that's an overly high market capitalization, but that's huge. Those multiple companies happen to be pursuing a quantum computing architecture that's based on trapped ytterbium ions, which is not the same thing as a trapped ytterbium ion clock, but it's pretty darn close. And so for us, global us, the entire clock community, not to be leveraging potential investment or asset or a lever of the quantum computing market might be leaving something on the table. So for those of you interested more in quantum, I really recommend attend Richard Overstreet's tutorial tomorrow. He's going to talk from Microchip. He's going to talk a little bit about that clock architecture and how it relates to quantum. So I put a plug in. I hope you can attend that tomorrow. I'm so glad Alex talked about autonomous vehicles, AI, and self-driving cars today. Not all of those things will require an atomic clock on them. Remember, time transfer is good, but many will. And to the extent that the low-cost clocks that we need from DoD may also be relevant for future sensor systems in the commercial industry is potentially also underexploited. Oil and gas, and many others. That's one recommendation. Number 2, it's important to fund the practical R&D necessary to develop these capabilities. There's a big gap here that's not being addressed. So academics are interested in fundamental physics and gravitational redshift and publishing in high-profile journals. They're looking at high-performance optical clocks. They're looking seriously at post-optical clocks, nuclear clock transitions. Industry cares about, let's make something better by factor of 2, whether it's Tempco or Power or Retrace or something. And there's this big, big gap here in the middle where the research isn't quite interesting enough for junior faculty to look at it, and industry doesn't have the resources. This is fundamentals associated with rubidium and ytterbium lamp physics, fundamental ion trapping problems, developing of photonics and UV lasers, miniature components. This is a small community, often funded by small business innovation research grants or FFRDCs, and more investment here will help the entire quantum industry in terms of moving forward. Number 3, we need to think holistically about the entire quantum ecosystem, right? So right now, we mostly have Ph.D. physicists working on these problems. There's a big gap at the associate's, bachelor's, and master's level for folks who want to be able to work in this technology. And there's something really interesting happening in university right now. We're starting to see a new departments or minors or like even just academic concentrations pop up. They have different names. They might be called quantum science or quantum engineering or atomic engineering, quantum computing, the field doesn't have a name yet because they're being developed. But it's important to start developing folks in the engineering college rather than the College of Liberal Arts who are getting less than a Ph.D. to be able to work in this area. In addition to people, we need factories to build stuff, particularly in the US when we talked about building sensitive subcomponents. There's a wonderful analogy to AIM Photonics, which is a recent public-private partnership developing lasers and photonics-based components, primarily in silicon photonics, that could be exploited to develop different material systems outside of silicon that we need for the integrated photonics, MEMS, ASICs, and other things that we need for these future quantum components. Number 4, this connects back to my estimate of how to do those clock comparison charts that we talked about at the very beginning of this presentation. In order to track anything, we need a good way to measure our progress. So here's a problem that we see. Pick an atomic clock. I just made fun of 2 of them, SpectraTime and Microchip. These are rubidium clocks. You have 4 pages of information. It's okay. Tells you a little bit about what happens. There's a single number for linear drift, just a single number, as if everything follows that. A tempco is given over an enormous temperature range. It's not clear how linear that relationship is. A standard way of measuring retrace is not given. A lot of information is missing. Now go to a single op-amp. Analog Devices OP27, famous awesome. 20 pages of information. Okay? 6 beautiful pages of graphs of how an op-amp performs over voltage noise, or current noise, or temperature variations, or shock and vibe. Anything you want to know about this op-amp is here. In an earlier draft, I actually had slides of the op-amp charts because it was so much information. But we can't do that for atomic clocks, I think just because no one's asking for it. What we really need, and would be a huge contribution to the community, is a better and consistent method of time error prediction. What we did in all the approximations that we listed in the IEEE review article is an estimate. Like we're taking a deterministic number and then just adding a stochastic instead of plus or minus. There's many other approximations that make this a poor way to do it. It would be wonderful if there was a common format, detailed data sheet that would enable us to be able to predict time error, compare vendors, and predict clock behavior in the field. This could be done, for example, with an IEEE standard, such as a future iteration of IEEE 1193 or some other standard. We need something like nutrition facts for atomic clocks that tells you the basics of what you have. We want a radar engineer or a comms engineer to be able to look at a data sheet and say, okay, so if I discipline this thing to GPS for 3 hours, then I let it run, and then I change the temperature by 14 degrees and let it go for another week, what's the time error? There's not a great way of doing that right now because one reason because there's not a linear tempco and other information is missing. Leaving a lot of time for questions here, which is great. I'll conclude with my final thoughts and opinions on the topics we've been talking about. Number 1, we're not doubters. Clocks will get better. Human ingenuity is a real thing. That trend line is not static. It will continue to get better. But hoping for the impossible, or really, kind of predicting that this is going to happen with your product next year in volume is just as hard as it sounds. Instead, we see a lot more value by doing all the things as a community that we need to do to be able to move this whole trend line down. First, in order to know that we're getting better, we need a good way of measuring that progress. Second, we need people and widgets to do the progress. So developing the whole quantum ecosystem with staff education, workforce development, foundry and component development. Developing realistic goals, especially government goals, that adequately look at, incorporate, or leverage commercial interest, not from an altruistic point of view, but to keep the factory alive so that there will be future DoD capabilities, will also enable us to be able to make these improvements, which will enable a wide range of applications, some of which we don't even know right now. So I think I'm good on time here. I want to conclude by I've interacted with and appreciated discussions with a huge number of MITRE colleagues on this. The list is too long to name, so thank you to everyone, internal colleagues. And I've also spoken with a number of external colleagues to debate and discuss and get some of the material for this presentation. Many of you may be joining on Zoom or in the audience. Thank you very much. For those in the virtual audience, I do want to list my email address here. I'd be happy to take questions if you have any after the fact and engage in a dialogue. I'm looking forward to the discussion. Thank you.
Are there any questions?
You mentioned the need for a better function, a better way to evaluate clocks. In your paper, did you play with the obvious things like just keeping the drift or just keeping the tau term with a different tau? And did you get the same idea that they all lined up in a power law?
You mean not take the TDEV out and just have drift?
Yeah, play around with that.
We did play around. We
and
plotted.
Did it make a difference?
In fact, that's how we picked a day, because time error after a day is pretty similar to time error after a second or an hour. It kind of, the time interval doesn't really matter.
And
it's a very similar trend line.
Other question I had was, what specifically is the uses the oil and gas exploration industries use for clocks?
So the underground seismology market, what they do is they put a large number of CSACs near the ocean floor, and then they let out a big sonic boom. And then they time the pressure waves, the reactions, and based on the time of all those back reflections, they can determine if there's an underground cavity, which may be a good place to drill.
Hi, David. Thanks for the talk. I thought it was very interesting. Very relatable. Usually have a lot more trouble following clock talks, being from the navigation side. You mentioned something, it was in the passing, it said something about lamp physics, and I was just curious what that is, because you said you praised it as the next big thing, and I don't know what it is.
Oh, yeah, so rubidium lamp jumps, for example, I think Jim Camparo at Aerospace has done some work showing that that is one of the limiting factors in the high performance clocks that are used in GPS, which is the contributor to the clock error, although that term is small in GPS. There's some instability associated with the frequency and intensity of light coming out of lamps, which is not even fully understood now. It's still a topic of research.
I have a question on your, you don't have to show it, but you showed at certain moment the CSAC at $200 cost estimate of the, I imagine this is the gross estimate of fabrication for the cost, right?
That's a goal.
That's a goal,
That's
yeah.
what people
so
want.
I was wondering, what drives this goal? Because looking at the market today, from year to year, prices are going up, right? So margins are going up too. But then we got this goal of producing CSACs at lower cost. Which is the market behind driving this goal?
So we want to be able to put small CSACs that are cheap in portable situations such as GPS receivers. And in order to do that, to put them with a lot of people, they need to be cheap.
But what is the application behind that? Okay, GPS receivers, they exist everywhere. Is it a specific application? Is it autonomous driving? What is it, the application behind it? Because atomic clocks, miniaturized atomic clocks as we know them today, like MAX or CSACs, they got a huge range of access to all those verticals already. But is it a specific vertical that is driving this reduction of the cost on CSAC?
I don't know if it's a specific thing other than it would enable holdover for longer times if there was an atomic clock, a cheap CSAC rather than a quartz oscillator in these kind of handheld systems. That's a general answer, but that applies to a number of different mission scenarios. Sure.
Just one last question.
So, hi, I'm Marcos Pangro from KTH, Royal Institute of Technology. I had a question regarding what you said regarding time transfer and these cheap CSACs. There is a possibility that we will not reach the $200 target, right? So, in this condition, where will be the benefit in improving the time transfer? Because for some applications, instead of having distributed CSACs everywhere, we might have one very precise one in one location and improve our time transferability over other methods of PNT, not necessarily GPS or other communication infrastructure. What do you think about this direction instead?
I think that's very compelling, and to the extent that time transfer is good, we don't need clocks. This is really one of the themes of the field. Time transfer is good, and that results in a small number of companies that care about this. In the future, I see, the innovations in time transfer will continue to happen at the same rate as atomic clocks. We tried to sort of compare those, or is the rate of those, how are those progressing? And they're just really sort of different units and different metrics. So we didn't have a great way of comparing the rate of change in those two industries. But I'd love to learn more there. Great. Thank you. Thank you.
Thank you very much. So this concludes our keynote, and now we're going to move to the